So we would have our initial point of, it's not going to be a strong acid, right? So our pH is going to start off a little bit higher. This is our point number 1. And then we move on to point number 2. So point number 2 is when we're looking between the initial pH and equivalence point. And it's the slow and steady incline up towards where our equivalence point is. So knowing that when we have a weak acid with a strong base, we have salts that hydrolyze. Therefore, we have to not only consider the concentration of the acid, but we have to consider its conjugate base that's forming on the product side. And it ends up to be a Henderson-Hasselbach with a buffered pH solution. So we calculate this as a buffer using the Henderson-Hasselbach equation. And we recall that pH is equal to pKa plus the log of the ratio of the base over the acid that we're producing. So we just did that. And remember, the pH is equal to the pKa plus the log of the base over the acid. This is our Henderson-Hasselbach equation. What we end up seeing here is that we have a small change in pH here, and it's not that steep change that we had in the last one that was very, very pronounced. In this case, since we are dealing with buffers, buffers resist change in pH. So our equivalence point is not as pronounced in these weak acid, strong base examples. The third point that I marked here with the X is the equivalence point. And that's when the equivalent amount of the conjugate acid and its conjugate base has indeed equaled. So that actually is equal to the pKa of our solution. When I skim this over, because the salt hydrolyzes, and the endpoint is greater than pH of 7 units. Strong acid, strong base at the equivalent point equals 7. But because now we have to consider hydrolysis of the salt that's being produced, if I add a strong base to a weak acid, the equivalence point is actually over the pH of 7. So a greater than 7 equivalence point is how I can determine a pH slope if I'm doing a strong base with a weak acid. This is going to be greater than 7 at this point. And if I continue to add that strong base after the equivalence point, it's the base that's in excess. So in excess means that it's just the excess sodium hydroxide that's going to determine the pH. We do not use Henderson-Hasselbach, but directly calculate the excess amounts of base. So the negative log of the hydroxide gets the POH, and then we flip it to pH. So after the equivalence point, the pH is determined by the concentration of the excess NaOH. All right, so let's look at an example. Let's say that I have acetic acid and NaOH. All right, so this is going to form sodium acetate, C2H3O2, and HOH is water. So let's write our net ionic equation. What we're going to have here is our acid, our HC2H3O2, plus, remember our sodium is going to split, and it's going to be a spectator ion, so we have our plus OH to give us, again, sodium is a spectator, our acetate, C2H3O2 minus, and water. Notice that the acid-base conjugate pair creates a buffered solution. And remember that between point 1 and our equivalence point, this is my buffered solution. So I'm going to use my Henderson-Hasselbach equation to find out the pH. Because this is showing me that when I take that acid and add the base, my weak acid plus a strong base, it's going to create more base. Remember that our initial, point number 1, is just our standard Ka equation, where I take my Ka that I'm given is equal to x squared over the concentration of my acid, pull out the x, and take the negative log of that. That gives me my initial pH. In between the initial and the equivalence point, we use the Henderson-Hasselbach equation because we know that when we have our acid and we start at our weak acid with the strong base, that when that happens, we have more base added. So we need to then use our pKa plus the log of the base over the acid. And then above our equivalence point, we have excess base, and which is going to be similar to the other one with the strong acid, strong base. So we're just calculating the OH minus excess there. So to summarize, when we have a strong acid and a strong base, we just use stoichiometry. To determine the Ka, we use 0 milliliters for the base, right? And because when we are looking at that, we're just looking at the weak acid. So just the x over x, or x times x, so x squared over the concentration of the weak acid is equal to the Ka. When we are looking at this and using Kas, that's when we have a weak plus a strong, whether it's a weak acid and a strong base, or a weak base and a strong acid. The weak acid before the equivalence point, we first look at stoichiometry and then we use the Henderson-Hasselbach equation. And again, that's similar to what we did in this last section where we're looking at buffered solutions. The weak acid at the equivalence point is simply equal to Kb, and the weak base after equivalence, that means that there's leftover strong base. Let's look at an example. All right, so we want to calculate the pH of the solution when we have 45 milliliters of sodium hydroxide, which we know is a strong base, added to 50 milliliters of 0.1 molar of acetic acid, and we're given the Ka for acetic acid. If we hadn't been given that, we could have found that in Appendix D. So let's write the chemistry here. We have NaOH plus acetic acid, and this is going to be a double replacement reaction, so I'm going to have sodium acetate plus HOH, which is water. We're told that we are given 45 milliliters of our NaOH. So I'm going to just draw a line under here. 45 milliliters of NaOH, and it is 0.1 molar. We're given 50 milliliters of our acetic acid, and it is 0.1 molar. So let's figure out, let's change this into moles. Again, we want to look at the stoichiometry. If it was a 1-to-1 molar solution, that would be fantastic. So we're going to change this milliliters into liters, so 45 divided by 1,000 to give me 0.045. 0.045 times the molarity should give me moles, 0.0045 moles. And I'm going to do the same thing with this one. I'm going to get 0.0050 moles. So we can see that this is not a 1-to-1 ratio. It's a 45 to 50 mole ratio. And so we can tell that this is going to be my limiting reactant. NaOH is my limiting reactant because we know that our reactants use up. So this is going to get completely used up, minus 0.0045. So I'm left with no NaOH. Minus 0.0045, I'm left with 0.0005 moles of acetic acid. And I'm actually going to write down this underneath 0.0005 moles of the acid. Now, let's think about our sodium acetate. Initially, I had no products, and remember, we're not including water. And since we are losing reactants, we are gaining products. So we are gaining plus 0.0045. So we have 0.0045 product. But we also know that this hydrolyzes. So the fact that it hydrolyzes is telling me that this acetate, assuming that we know that sodium is going to be a spectator ion, sodium is going to be a spectator ion. So when I have my acetic acid plus hydroxide, it's going to create more acetate. So it's not one of our strong and strong where that completely 100% dissociates. This is showing me that I am producing more base, 0.0045 moles more base. So let's plug this in. First, we can see what our initial, well, actually, the pH of the solution formed when we add all of this together. So we have no hydroxide left here, but I've got 0.0005 moles of my acetic acid, and I have 0.0045 base that was produced. So we're going to use our Henderson-Hasselbach equation, which is the pH, the negative log of the Ka, which we're told is 1.8 times 10 to the negative 5, plus the log of our base over our acid. And we can do one of two things here. We can just use our mole ratios in this case, since it's 1-to-1 ratio. We can do my base, my acetate, 0.0045 over 0.0005. And again, this is my, I'm just going to put in parentheses here, my acetate, my C2H3O2 minus over the acid, HC2H3O2. Okay, so let's see what we get there. We have the negative log of 1.8 times 10 to the negative 5th plus the log of 0.0045 divided by 0.0005. We get 5.70 for our pH. Now, we could also use the molarity units. This is moles. We could do moles per liter. We just need to be conscious of how many liters we have. We have 45 plus 50, so we have 90 milliliters with, 45 plus 50 is 95 milliliters. So we would divide by 0.95 liters for both of these, 0.95 liters. But it shouldn't make a difference since they're both the same. It would be like saying both of them divided by 1. But that's okay. We're going to do that just to make sure that everything works out. So if I do 0.0005 divided by 0.95, I get a concentration of my acid as 5.26 times 10 to the negative 4. So I'm going to just redo this one down here. The log of base over acid. So my acid, 5.26 times 10 to the negative 4. And then let's look at my, that's big M. I'm going to put an arrow, let's see, over here. 5.26 times 10 to the negative 4, big M. And for my base, I'm going to put an arrow over here, 0.0045 divided by 0.95, and I'm going to get 0.00474 big M. So if I do my 0.00474 big M, again, that's my base over my acid. So just to prove to you that we get the same number, I'm going to do the negative log of 1.8 times 10 to the negative 5 plus the log of 0.00474 divided by 5.26 times 10 to the negative 4th. And we get 5.70. So you can either use that mole to mole ratio, or we can do it divided by that total volume that we were given, 50 plus 45, so 0.95 liters. Either one of those works, but we get a pH of 5.70. Let's look at another example. Calculate the pH in the solution formed by adding 10 milliliters of 0.05 molar NaOH to 40 milliliters of 0.025 molar benzoic acid. We're given the Ka of benzoic acid, telling me that it is a weak acid. And we, of course, know that NaOH is a strong base. So let's write this down and see what chemistry we have. NaOH plus benzoic acid. I'm just going to write it as HA. And it's going to form an equilibrium. And we know that I'm going to have HOH, we're going to have water formed, and we're going to have sodium benzoate. So we're just going to say Na. And we know that those NAs are not going to have anything to do with this equation. We're going to have A minus over here, OH minus right there. Now let's write down that we have 10 milliliters of 0.05 molar. And then of my acid, I have 40 milliliters of 0.025 molar benzoic acid. And we also know that when we have a strong base, a weak acid, it's going to form that conjugate base. It's going to form the salt, sodium benzoate, and that salt is going to hydrolyze, right? So it's going to make that buffer. So we're going to write down buffer. So let's look at our before. How many moles do we have? So I'm going to take milliliters and turn it into liters and make that 0.01 liters times 0.05 moles per liter, and I get 5 times 10 to the negative 4th, where if I wrote that in standard form, 0.005 moles. And I'm going to do the same thing with 0.025 molar times 0.04 liters, 0.001 moles. And it's a 1-to-1 ratio. So we're obviously going to consume our NaOH first because it's the smallest amount. So I'm going to consume 0.0005 moles, and we're left with none. So this is my limiting reactant. If I minus 0.0005 moles, I'm left with 0.0005 moles. And then that also means if I'm using these up, I am creating some of that base, that conjugate base, so plus 0.0005 moles. All right, so now when I plug this into my Henderson-Hasselbach, I could do one of two things. I can use these mole-to-mole ratios because I know that it's a 1-to-1 ratio, or I can divide and find these molarities because it's moles per liter. I've got 40 plus 10, I've got 50 milliliters. So I could make that into liters and divide both, but it doesn't matter, we can do either way. So let's plug it into our Henderson-Hasselbach. We know that our pH is equal to the negative log of the Ka that's given to us. We could also find this on our Appendix D, 6.3 times 10 to the negative 5, plus the log of our base, 0.0005, over our acid, 0.0005. When I plug this in, I'm going to do the negative log of 6.3 times 10 to the negative 5. And then if we notice, these are the same values. They're going to cancel right out. So I'm just left with a pH of 4.20. Again, when I have a strong base and a weak acid, we know that it's going to form a salt that is a buffer solution. That salt is hydrolyzing, so it is creating more of that base. So here we can see that, yes, I had my limiting reactant was my base, and I had excess acid, although because of that hydrolyzing, we created more base. So I had to use, first I had to do the stoichiometry, and then I had to use Henderson-Hasselbach. Let's look at a problem that includes a weak base. So we want to calculate when we have HCl, which is our strong acid, with NH3, which is a weak base. So we know that our strong acid is going to 100% dissociate. So when I add these two together, I'm just going to have H plus my weak base, NH3. And we know that it's going to create NH4. All right, NH4 plus. So let's look at what we have. We have 10 milliliters of 0.1 molar HCl. 10 milliliters, 0.1 molar of HCl, which is our H plus. We have 20 milliliters of 0.1 molar of our ammonia. All right, so we're going to do molarity times volume to get moles of each. So I'm going to do 0.010, which is 10 milliliters into liters, times 0.1 to get 0.001 moles. Then I'm going to do the same thing with this one. I'm going to do 0.020 times 0.1 to get 0.002. So this is what I'm starting with. And of course I have zero product. So again, I can see, well, which one's going to be consumed first? My H plus. So we're going to subtract minus 0.001. So my acid is my limiting reactant, minus 0.001. So I'm going to have excess ammonia, 0.001. And we know that this salt that's forming this buffered solution is going to be created, plus 0.001. All right, so now I'm going to look at, since this is my weak base, I'm going to look at Appendix D to find the Ka, which should be 1.8 times 10 to the negative 5. Now I'm going to plug this into the Henderson-Hasselbach. Since I have my base and my acid concentrations, I have my Ka, so I can plug it in to pH is equal to the negative log of, I need to find my Ka since I have, oh, that's not a Ka, what am I saying? This is my Kb, because it's ammonia, it's a base. So I need to find the Ka. And remember, we can find the Ka by doing our constant for our water are 1 times 10 to the negative 14th divided by the Kb, 1.8 times 10 to the negative 5, plus the log of our base of our acid, which they happen to be the same, 0.001. And again, remember we can use moles, or we could calculate the molarity. There's 20 plus 10, so it would be 30 milliliters, so we could divide both by 0.03 liters. But because we're doing it both by the same, because it's a 1-to-1, we can just use what we're given. So let's see what we get here. The negative log of 1 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5th. 9.23 should be our pH. And just to show you that this zeroes out, let's plus the log of 0.001 divided by 0.001. And notice that we get the same answer, 9.26 as our pH. 9.26. And just to go back and see if this makes sense, we know that we had excess base, right? So our pH being at 9.26 is on the basic end.